Think about it. What is the one field of physics that influences everything? From electricity to magnetism, from the tiny scales of the proton to the formation of huge galaxies. Yes, it's quantum physics. Welcome back to Scientific Curiosity, and today's episode is on the topic why quantum. So, quantum theory started way back in 1900 and it stemmed from one of the unsolved mysteries of the time. What happens when you heat an oven? It was observed in the days of yore that when objects like metal, for example, were heated, they emitted light. These objects were theoretically known as black bodies, even though they necessarily weren't black. Light was also assumed to be a wave, as shown by the double slit experiment and Maxwell's equations for electromagnetism. Also, the higher the temperature, the higher the frequency of light emitted, in average. This was known as blackbody radiation. But, as usual, there was a problem in this thought process, and the problem was in predicting the frequencies of light emitted and with how much intensity they were emitted, given a particular temperature, of course. By 1900, the dawn of the 20th century, there were two models to do the same: Wien's law and the Rayleigh-Jeans law, also which I will call as the R and J law. Wien's law worked very well for high frequencies of light, and R and J worked very well for low frequencies of light. But apply Wien's law to low frequencies and it was a mess. Apply R and J to high frequencies and it was a catastrophe, an ultraviolet one, because it predicted infinite amounts of ultraviolet light to be emitted by the black body, which was just not possible according to the laws of physics. So, here's the situation. Enter Max Planck, the genius, orthodox game changer. He just wanted to prove his friend's Wien's law. Wien was his friend, and solve the black body radiation problem. So he imagined the black body to be made of very small oscillators, which are not to be confused with atoms. Planck hated those, which vibrated at a rate proportional to the temperature and emitted light proportional to the vibration, the rate of vibration. And he tried to find out the connection between the energy of these oscillators and their entropy. Huh? Enter what? Entropy. A huge confusing concept which even prominent physicists of the 20th century dared not question. I will discuss this in detail in later episodes. For now, here is the TLDR. It is a property of matter that depends on the randomness or disorder of the arrangement of the particles of that object. So this has a low entropy while this has a high entropy. The modern version of entropy, which is based on statistics, was developed by Ludwig Boltzmann, who was very underrated at his time but was a true genius. Planck hated that, trademark scientific curiosity. But continuing on, he found a new formula and it matched the experimental data perfectly. Here it is. Math. But this was phenomenal. Planck's law, as it came to be known later, was accepted by the physics community, but nobody knew what it actually meant. Nobody knew the physical reality of it. Planck put himself to work trying to find the physical meaning of the law, but he couldn't without using Boltzmann theory. Planck, finally letting go of his orthodoxy, used Boltzmann's theory, assuming light to be made up of small chunks just so that he could calculate the entropy. He later hoped to make these pieces so small that they would become wave-like, just a classic calculus problem. Surprise! He couldn't do that. No matter how hard he tried, he still could not get rid of the chunks. If he did, by doing some mathematical juggling, his law failed. It just didn't work. This was astounding. When the results were published, the entire physics community was shocked. Light was a wave, but now it seemed it was a particle, a quantum of light. Everybody, including Planck, hated this and they rejected it, saying it was just clever math. Everyone except one, that is. Enter everybody's favorite scientist and physicist, Albert Einstein, the one with the white hair and the wrinkles and the absent mindedness, except not. This is the young Einstein, still working in the Swiss patent office in Bern. The year is 1905, and young Einstein has a brilliant idea. He imagines a box with waves in it and he compresses those waves to a smaller volume inside the box. Now, of course, the entropy of these waves changes and he tries to calculate this change in entropy. What he observes is indeed very exciting. The changing entropy is the same as he would observe if he replaced the waves with gas particles. From this, he deduces that light indeed is made up of particles. He applies his new insight to another unsolved problem, the photoelectric effect, aka when electrons escape metals after they absorb light. The thing was that if you send lots and lots of red light, electrons won't escape at all. A little of blue light though, voila, free electrons. But no sensible explanation though. Einstein came in with his new light is a particle idea and he resolved the photoelectric paradox. He explained that the particles of blue light have more energy and hence absorbing them gave the electrons enough energy to escape its atom, while red lights have low energy so the electron just absorbs it and just releases it out. Okay, weird analogy and fun fact. Weird analogy first. Think of the electron as a dragon eating people, the people who are analogous to light. The people dressed in red, corresponding to particles of red light, are weak, and when they are eaten by the dragon just spits them out because the dragon finds that they cannot fill its stomach. But the strong ones are those who are dressed in blue, corresponding to the the particles of blue light, and they are strong enough to give the dragon enough strength to escape the city and go wreak havoc somewhere else. Whoa, that's dark, pretty dark. After that, you deserve two fun facts. Albert Einstein proved atoms exist. That meant particles of light are called photons. Einstein's paper convinced lot of physics and just hobbyists that light was a particle. It was just as groundbreaking as Planck's work. Planck, who was in charge of selecting papers for publication in the journal that Einstein sent his paper to. Wait, what is a journal? A journal is a sort of a monthly magazine in which scientific papers and magazines are published. Scientific papers and findings are published. And Planck was in charge of selecting papers for publication in the journal Annalen Physik, and Einstein sent his paper there. But Planck did not like it. But still he allowed it anyway because he knew it was pretty good. This paper would eventually lead to the paradigm shift known as quantum mechanics. Next time, we delve deep and talk about how the atom was discovered and how the pioneers of quantum physics constantly updated the atomic model and how it changed physics in ways unimaginable. Thanks for watching this episode of Scientific Curiosity. And by the way, while you're still here, did you know that matter can bend space-time around it? Well, you can do the same to the YouTube algorithm. If you liked this video, which I probably hope you did, you can like, share and subscribe. Stay tuned for the next episode of Scientific Curiosity and thanks for watching.